So we're going to be talking about capacitance. Capacitance is the ability of an object to store charge. And there are many practical uses of a capacitor. Perhaps the most common and most relatable would be a Kodak disposable camera. Now when you press the flash button on the front of the disposable camera, I don't know if you youngins know that much about it, but then it would get power from the battery to a capacitor, which would then light up that little red light on the front, and once it's lit up, that means that the capacitor is fully charged, and so when you click, that would release all the energy stored in the capacitor to the flash bulb. Then you get the flash. So basically that time that took for that red light to completely light up would be the capacitor charging, which we'll talk about later in this lesson. So basically how capacitance is defined is by this little doohickey line right here. Alright? We're going to graph delta V as a dependent variable. So that means that, or independent variable, rather, right? Yeah. Okay. And charge as the dependent variable. So as we increase delta V, we'd be increasing the charge on the plate, or on the capacitor. So that means that the slope of this would be Q over delta V, which has been found to be the capacitance of whatever object you were doing this to. So Q equals C delta V, and that's a very general equation that's used in many contexts. Alright, first of all, I'm going to talk about different capacitor geometries. The most common of which is the parallel plate capacitor. Now, how this looks and is generally represented is like this. And you'll see capacitors in circuit diagrams are drawn like that. And generally, if you have a current, initially when you're charging the capacitor going across this parallel plate capacitor, you're going to have the positive charge from the direction the current's coming from and the negative charge building up on the other side. And in here you're going to have an electric field going from positive to negative. And you know from electrostatics that all electric field lines start at positive and end at negatives. So that follows the current. So now we're going to derive the capacitance of this parallel plate capacitor. So we have a few equations here that are going to come in handy when we're doing this. So first off, I'm going to define what the charge is on this plate, because we don't necessarily know what the charge is exactly. So we're just going to use density notation. So I'm going to say sigma, which stands for surface density or surface area density, equals Q total charge over A. And this Q we don't necessarily know. It's not a definite number. So now we're going to plug in here. We know that from here that our Q enclosed on this plate will be sigma times A. So we'll plug in for that. And we know that the integral of dA is just going to be A. So we'll just say this is A, which then cancels out over here. So we get E on this cap equals sigma over epsilon naught. And for reasons that will just make it easier later in this derivation, I'm just going to throw back in this for sigma. Okay. So now we're going to use this delta V equation with the equation we just derived. So we know delta V equals E, and since there's no sort of variable that's changing in here, this is just a constant which we can bring out that E gets out. And the line integral is going to be from 0 to D, where D, which I should have mentioned earlier, is just the distance between the two plates. Sorry. So that's just going to equal ED, which is then going to equal, mess that up, QD over A epsilon naught. So now we have delta V. We can just plug into here to get the capacitance. So we get C equals Q over QD over A epsilon naught. And since we know math, we can just, this thing's going to go on top and this is going to stay as a denominator. So it's going to be QA epsilon naught over QD. Q's cancel out. And we see that capacitance for a parallel plate capacitor ends up being epsilon naught times A over D. So the only two things that matter in this type of capacitor are the area of the plates and the distance between them. So just simple geometry. Now, what I'm going to be talking about is this dielectric constant, which comes into play with capacitance. Now, dielectric constant basically determines the permittivity of the space in the capacitor, which in this parallel plate capacitor, just this little empty space here. So basically, permittivity is determined by epsilon naught, but if you multiply epsilon naught by k, you're going to get the actual permittivity of that free space. And so kappa, you can derive by dividing the capacitance of the capacitor with a dielectric substance in it, which I'll discuss in a minute, over the dielectric of the capacitance in the vacuum. So the dielectric constant of a vacuum is 1, which is just the definition of dielectric constant and how vacuum dielectrics work. Then for paper, if you put paper in between two parallel plates, that would basically multiply the capacitance by 3.85. Then if you put one of the highest ones is calcium copper titanate, which is greater than 250,000 for kappa. So basically just know that to get any capacitance with a dielectric inside, you just multiply whatever your capacitance equation is times the dielectric. So basically, if we were to get CK for this, you just multiply this by kappa. Okay, so two other capacitor geometries that are common, but not nearly as important as parallel plates, are the cylinder and the sphere. And now I wrote out the proofs here, but I'm not going to go through them. Basically, for cylinder, you just have to remember linear charge density, which is just Q over L, and use all of your standard integration. Go from E to V, then plug it into C equals Q over delta V, right? And the sphere, I just skipped the Gauss's law because we know the general electric field for concentric conducting spheres is Q over 4 pi epsilon naught r squared. And then you just go through this derivation here, and you arrive at these two. So just know how to derive these. If you just go over these multiple times, you'll get the gist of it, and it's just very monotonous. So I thought I would go over it because they aren't nearly as important as the parallel plate. And just remember that you multiply by kappa for your dielectric constant for both of these. Alright, the next thing I'm going to talk about is when you put caps in circuit. Now we're going to figure out what exactly the pattern is for when you have them in series or in parallel. Now, when they're in series, we know that the voltage drop here, when you compare it to our equivalent circuit here, the voltage drop over all three caps must equal the voltage drop over that one cap. So we're going to say, because the EMF in both of them is equal. So we can make this statement here. And now we're just going to try to find the equivalent capacitance. So we're just going to plug in for a number, or plug in an expression with C in it, which is just Q over C equivalent. And we know that the Q on all of these must equal each other, and must equal the C or the Q on the equivalent circuit. Sorry, because they're all experiencing the same current. So we're not going to get a certain percentage of the charge. We're going to get the same amount of charge once all caps are fully charged. So we're just going to put in Q for all of them. And then we could just cross out the Q's because they equal each other, divide by Q. And then we get 1 over C equivalent equals 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3, and so on. And I'll write it in sigma notation. So equivalent capacitance equals 1 over the sum of 1 over C sub n from 1 to n. Or basically you just add the reciprocals of all the capacitances and then flip that. Just remember you can't flip this whole equation over because this is a sum. Now when they're in parallel, it's a little bit different than this, right? We know that when things are in parallel, that means that the delta V is, I'm going to go over here, that the delta V on each of them is equal, so we'll just write out that statement first. And that means that this must be equal to each delta V here because it has the same epsilon, or EMF. But we know because of the junction rule that not each of these is going to experience the same amount of current, and therefore the charges, once each capacitor is fully charged, it's going to be different. So that means that the sum of the charges on all three of these capacitors will equal the charge on that capacitor. So then we can just write out a statement here. Since we have this sum, we'll just plug in here for with C and delta V. So we know that our charge equals C delta V. And since delta V is equal, we just get the sum of all the capacitors equals the total capacitance of the circuit. And in sigma notation, you get that. So that's how you find the equivalent capacitance of a circuit. Alright, now that we know how capacitors operate in circuit with each other, we're going to learn about RC circuits. Now this is the simple RC circuit. You have an EMF here. That's good enough. Then you have a resistor and a capacitor, and generally it'll flow to resistor first and then capacitor, and there might be a switch involved in front of the resistor because it goes from positive to negative. Okay. So one thing you should know before we get further into RC circuits is the time constant, or tau, which is a nice little turbulent T here, right? Which represents torque and mechanics, but in our context it's going to be for the time constant of a circuit. And it just equals RC. And if you were to actually put the units in, which I'm not going to do, for resistance and capacitance, like the basic units, like resistances in Newton meters per amp, then you'd end up with this equaling seconds. And I'll show you a little bit later what exactly that time constant comes in handy for. Basically, when the purpose of an RC circuit is to control how much charge is getting on the capacitor over a given period of time. So basically it's slowing down the charging of the capacitor, but the capacitor gets charged nonetheless, so it's not just all going to go straight to the capacitor from the EMF. A common usage of this would be in car doors with the lights and whatnot, like how you close the door and then the lights sort of fade away. That's the purpose of this, except the resistor would be on the other side while it's discharging the energy stored in the capacitor. Now, when you're charging an RC circuit, you know that the voltage, once you finish the entire charging process on this capacitor, is going to equal the EMF. Because when that thing is completely charged, no charge is going to be moving across this dielectric, so you're basically going to have zero current. So essentially, you're going to have like a graph for delta V over time. It's going to go to a limit like this, where this is your EMF. And similarly, for charge, it's going to have that sort of thing, except it's going to be capacitance times your EMF. Right? So I'll just write that out. And then for current, since we know that it's going to be 0 once that t goes to infinity, it's going to start at some value, which is just going to be your epsilon over r, right? And then it's going to decrease to 0 as t goes to infinity. So we'll just come up with a couple of equations that will explain these phenomena well. So delta v equals epsilon Alright, now basically how this sort of thing works is that it reaches a limit. Now think about it, if t approaches infinity for e to the negative t over whatever, then that e to the negative t over whatever as t approaches infinity is going to approach 0. So this is 0 when t equals infinity, which is somewhere off here. Now this is just going to equal 1, this thing in parentheses, then you're just going to get your initial charge and your initial voltage. So that's what the limit is. It's never going to actually touch that limit, but it's going to get, infinitesimally close to that limit. In terms of current, we know that if it's a negative exponential, that's going to be decreasing towards, y equals 0 as t goes to infinity. And as this approaches infinity, this equals 0, so this whole thing equals 0. But when t equals 0, we know that this is just going to be 1, and so it's just going to be epsilon over r, which is the total current. If there wasn't a cap in there, just an r, then that would be the current running through the whole thing. And similarly with this, when t equals 0, this thing equals 1, or e to the negative 0, e to the 0 equals 1, so 1 minus 1 equals 0, charge and voltage on the cap equal 0.
That's a wrap.
So now when we're discharging the capacitor, now what happens when you're discharging an RC circuit? These equations apply to when you remove the EMF. So let's say you remove the EMF, and then you flip a switch that you place in where this EMF is, so that way all the charge will start flowing around to create an equilibrium. Well, we know that there's going to try to be a 0 voltage drop on this current, on this circuit, because that's the goal when there's no EMF. You want to reach an equal voltage across the circuit. So that way, delta V will be 0 on the cap and on the resistors. It's going to distribute the charge. So this would make sense because we know that the voltage initially on this capacitor when we're flipping the switch, right when you flip the switch, when t equals 0, equals E, which makes sense because this will equal 1, or epsilon, and then as you approach infinity for t, then it's going to approach 0 on the cap. Same thing with Q. You have maximum Q when you flip the switch at time t equals 0, which is C epsilon, but as you approach t equals infinity, you're going to get a charge of 0 on the cap. And then same thing for current I. It's going to be initially, since the delta V is going to be maximum, and you have an R right there, it's going to be the same equation, or same initial current, and it's going to decrease to 0 as t approaches infinity as delta V approaches 0. Now I'm going to talk about something that's a little bit more obscure, but it will come in handy, and they're called CC circuits, which is basically where you have 2 caps and a switch. Now generally what they're going to say on an AP problem would be like, capacitor 1 is fully charged outside the circuit, an isolated circuit with an EMF epsilon or whatever, or it's going to give you the capacitance or whatnot. So we know, therefore, that Q naught on this, the initial, we'll just say Q naught, or naught applies to the initial condition of this capacitor, equals the capacitance of this capacitor times delta V naught, where delta V naught equals epsilon because it's fully charged, which we just discussed over here. So now, since we know that, another thing we know is that this, when we flip the switch, this whole circuit wants to reach an equilibrium. So for it to be equilibrium, since it's in parallel, the voltages across the two caps will be equal. When they're fully discharged, charged, this one's going to be discharged and this one's going to be charged, but they're going to have, still have both, this one's still going to have charge on it, but less. So we know this, and just by knowing this, you can basically assume a lot of things depending on what the problem's asking for. Another thing that'll come in handy related to this is and so because you're not really losing any of the voltage drop across the circuit. It's going to have the same voltage drop if you go around it once the circuit's closed, but they're going to have different voltages, and they won't be the same. It won't be just 2 times delta V1. They'll be different. And basically, if you know this and know how to find your equivalent capacitance, then you're all set, depending on what they're asking for. They might ask for energy, which I'll talk about in a minute, or they might ask for the charge on this thing when it's finished. And so then you just plug in here, you know, from that statement above, and then you just plug in more stuff. And let's say they're asking for Q2. Well, if they give you capacitance 1 and they give you this, then you can figure out what that equals. And then you can figure out what this equals sort of by that way, because you're going to also know what cap 2 is equal to. And you just have to summate these two. So that's CC circuits. Now the last thing I'll discuss is the energy stored in a cap. Now we're just going to use a basic definition of electrical energy to start us off. We know that voltage units are joules per coulomb. So we basically know that V equals work or potential energy over charge. So from that sort of definition, or just from your general knowledge of electrostatics, we can derive that equation. This is just the general equation for V will be du over dq, right? So now we're going to integrate this, but we're going to sub in for V first with something that involves capacitance. So we'll just put in Q over C equals delta V dq. Now if we're going to integrate this, this doesn't need to be having any limits of integration, but this one will go from 0 to the maximum charge Q. And now if we solve this, we get U capacitor equals 1/2, or 1 over 2C, put that there, over, or times Q squared, 0 to Q. So we get Q squared over 2C. Little interruption there, okay. So we get that the potential energy of a capacitor equals that. And basically you can just plug in a few, whatever definition of capacitance you need. There are 3 different equations that are equivalent to this. Let's write them out. And basically if you just plugged in for Q here, you'd get Q equals C squared times V squared, get that. And then if we plugged in for C here, C equals Q over V, and then you get that. I mean, I don't have to write that out for you, right? This is the most common form you'll find this in. That's the one they give you on the AP equation sheet. So if you know that and just know general, equation for capacitance, you know the potential energy that's stored in a cap. Now, keep in mind, this is when the capacitor is fully charged. So you need to know, basically the V is going to equal epsilon, or the Q is going to be the maximum Q when it's fully charged, etc., etc. Now, if you wanted to find like over a period of time before it was fully charged, and you were trying to find out here, then you'd have to integrate that area, and you'd have to figure out what the Q is up here and whatnot, right? But just use the same integral. This is the derivation of it, This is when it's fully charged. Keep that in mind. Now that is capacitance. That's a lot of information. Just very important part of circuits and electrostatics.